Well, that last problem for lifting water, aka a pumping problem, was fun, so let's kick it up a notch in terms of difficulty. Because let's face it, real swimming pools aren't really a box. They're not a rectangle, as the previous example would suggest. What's more realistic would be have a pool that has some changing depth. So we're going to have it go from 1 meter deep here down to the deep end, which is 2 meters deep. And then we want to know how much work is required to pump all of the water. If it was full up to the top of the pool, so the water is all the way up to the top, how much water or how much work would it take to pump all that water out? And we're just going to pump it to the top of the pool, as you can see here. So we're not going to go 0.2 meters higher or anything like that. Okay, I think it'll help us in this particular instance if we look at a side view of the pool. It's not really going to be to scale, but bear with me here. Okay, so if we look at it from the side, we have one section, and then we have another section. And we're assuming, oops, I think I did that pretty well. We're assuming that that's a nice even slope. You can see it kind of right there on the graph or on the drawing that it's a nice even slope. Okay, so this from here to here is 1 meter, and this from the here to here is 1 meter. Now it would be smart to establish y equals 0 at the bottom. That would just be wise. All right, then we know that this value right here would be y equals 1 because that's 1 meter higher, and then this would be y equals 2 right here. So if you think of where y is, if you have, I don't know, water at this level, it doesn't really make any difference. So if we say that that's y, here, actually, let me do it this way. That height right there is from here to the bottom is y. Then this height here that you have to pump the water out is 1 and 2, 2 minus y. Well, there it is. I mean, that's a lot of what we need right there. But there's one other piece, which is that the water works differently on the top than it does on the bottom. So we're actually going to find two volumes. We're going to find a volume for the top part, so like volume 1, and we're going to find a volume down here, volume 2. It doesn't change the y and the 2 minus y. I mean, the 2 minus y is just, it is what it is, right? But it will change how we think about it. Sorry, that was too small, so let me get that in a little bit better. There we go. Okay, so let's think here. I'm going to leave myself some space just in case I need it to figure some stuff out. Now, the work, the total work, would be equal to the work it takes to lift volume 1, right, that first section of water, plus the work it takes to lift volume 2. Right? So we have the section of the pool that's like a big rectangle, big rectangular prism. And then we have the section of the pool that's not like a rectangular prism, that's more like a wedge. All right, so I have to deal with them separately. Now, volume 1 is actually pretty straightforward. So let's do volume 1. So volume 1 would be up at the top. It's going to go from y equals 1 to y equals 2. So from 1 to 2. And then it's the same thing. Oh, let me just write this formula in here. I'll just put it up here. Remember, it's A to B, rho G, A of Y, D of Y, dy. Just a little reminder. That's the general form. Okay. So then if that's the general form, then volume 1 would be from 1 to 2, because we're going from the middle of the pool up to the top of the pool. And then, well, rho is 1,000. G is gravity, which is 9.8. Like, those two don't change. A of y, well, the top part is a big rectangle, right? So A of y is pretty straightforward. A of y is just 20 times 10 because it's a rectangular prism, like a big box, like the last problem was. So it's 20 times 10, no problem. Never changes. So 20 times 10. And then d of y, we already said, was 2 minus y. right? So this is A of y right here. This is D of y right here. And then, of course, this is rho and G, right? And then dy. Just throw on a dy on there. No problem. All right, so that part's easy. That's actually pretty much the same thing we already did before, except we're only going to 2 because we're only going to the top of the pool. We're not going to like 2.2, get it 2 meters above the top of the pool. Or actually, that would change this part, not that part. That would stay 2 because that's the top of the pool for the water. If it was going 0.2 meters higher, that would be change this number right here, the depth, right? But we didn't. We're just pumping to the top of the pool. All right, so that one's easy. Where we're going to run into a little bit of trouble is on the other part. So for volume 2. Sorry, that looks like a 1 and 2. What I mean is volume. All right, so the y coordinate's not the hard part, right? We know that it's going to start here at 0 and go to 1. So we're talking about this bottom part of the pool. It's kind of like wedge shape down there, right? Okay, so we're going to go from 0 to 1, no problem. The 1,000 and the 9.8 are never changing because this is water and it's earth. So because it's water and earth, there you go. Now the area, I'm going to have to figure out. That's the part where it's going to take some doing. But I know that the depth is still 2 minus y, and I know it's still dy. So that hasn't changed. Sorry, that doesn't look like a minus. There we go. A of y. A of y is where I need to do some work here. So let's look at kind of a cross section of let's look at the bottom part of the pool. Let's look at it again. So we have kind of, I'm not going to draw it to scale here, so just bear with me here. So if you think of this side right here, right? And then it kind of comes up. Does that? I'm looking at it slightly at a different, it's not quite a cross section. It's not quite a thing, right? Now, part of it I know never changes, the 10. Right, the 10 is just set in stone for the whole pool. So this is 10, this is 10, it's 10 all the way along. So no matter where I cut into it, it's 10 wide, right? But the question is the length, right? So if this is y equals 0 down here, and this is y equals 1 right here, then I need to be able to figure out for any y in there. So let me pick a y. Right there, then I have a depth of water in the pool, right? And I have a cross section. It would be like that. So I need to figure out a relationship here. Let's think about this. When I'm at y equals 1, that little rectangle of water would be up here at the top. So the width would be, let me do this. The width would be, or no, not length, width, length. The length would be 20 up here. But down here at y equals 0, the length would be 0, right? All right, well, think about this in another way. What if this was 0.5, right? If this was a half for your y value, then this would be a half of 20, which would be 10, right? So, and now keep in mind the width never changes. The width is just 10 all the way down, right? This is 10 no matter what. So width is 10, 10, 10, never changes. So then what's the area? Well, the area up here would be 200. The area down here would be 0. The area in the middle would be, let's think, if this is at height of y, then this comes out to 20y, right? There's a relationship here. Let's put it another way. Look, I know that the bottom goes 0, 0, right? Or 0, 0. And then I know the top goes 120. And I know it's linear in between, right? I can tell this is a straight line. So if I want to think about length in terms of y, so if I want to make a relationship here, let's go this way. So this is the y height. So if I go y to length, 0, 0 to 20, or 1 and 20, then I know that this value, this length, would be equal to 20 times whatever this value is. So that's why I said if it was 0.5, so if I make this 0.5, I'm halfway up. So that means I'm halfway down this slope. And so that would make this side right here 10. So it'd be 10. It'd actually be a perfect square, which of course is not the way I've drawn it, but that's the way it would be. You can kind of see it better up here, right? If I'm halfway up, go halfway across, and you're in the middle of the pool, and it's a perfect square, right? You can see it that way. Okay, so area is length times width. The width we know is set in stone at 10. The length, what I'm trying to make an argument here, is that there's a relationship here. So length is equal to 20 times y. Whatever your y value is, whatever your height is, you'd multiply it by 20, and that would give you the length. So if I'm all the way at 1 meter up, it goes the whole length of the pool. If I'm a half meter up, it goes half of the length of the pool, right? Which a half times 20 would be 10. If I'm down at the bottom at 0, it would be 0, and it'd just be a line. Right? In other words, you can make a linear relationship out of these points. So that makes this 20y, which means area is 200y. Right? I'm just making notes for yourself because that'll be the hard part to figure out. Will be to figure out that relationship. And the key is that this is a diagonal line. Because it's linear, then you can figure out this relationship. At 0, it's 0, it's 1, it's 20, and it's consistent all the way up. All right, area is length times width, which is 20y times 10, which would be 200, because the width never changes. That pool is always 10 wide. And that gives me what I can put right in here. I can go 200y. That's the area for volume 2. And of course, the depth never changes, right? That was 2 minus y. We figured that already. But there's the area for the second part, the deeper part, as a function of y. Now, once we have this, it's easy peasy. 9.8 times this, times 20, times 200 is, let's see here, drum roll. Okay, so let me go down here. 9.8 times 1,000 times 200 is 1,960,000. Okay, so this is 1,960,000. That takes care of this and that, right? All of that goes out in the constant. And that leaves me the integral of 2 minus y. The integral of 2 minus y is 2y minus 1/2 y squared. And we're going to take that from 1 to 2. So in other words, all of this part became that number right there. Similarly, it's actually going to happen over here also. There's a 200 times, so that's a constant. So I can actually pull that out in front here and make it 1,960,000 there as well. And then we're going to integrate, I'm going to take another step here because I'm integrating, well, actually, let me just do it right here. These two pieces together make 2y minus y squared. So I'm integrating 2y minus y squared. It'd just be easier if I can do both integrals in the same line. The integral of 2y is y squared minus 1/3 y cubed. I'm going to take that from 0 to 1. Okay, so obviously I can pull a 1,960,000 out of the whole thing because both of them have it. And then I can just find what 2 times 2 minus 1/2 times 2 squared. I'll take all of that minus, and then a 2 times 1 minus 1/2 times 1 squared. Figure that out. And then all of that is plus. So there's a plus in there. And then, well, we don't have to worry about the 0. The 0 is not going to do anything for us. But the 1 is. So it's going to be 1 squared minus 1/3 1 cubed minus 0 if you want to see it. Right? Because the 0 doesn't do anything for us. Okie dokie. So this is 1,960,000. 4 take away 2 is 2. Here. That's 2. Minus 2 take away 1/2 is 3/2. And then, let's see here, that's a minus. 1 minus a third is 2/3. There we go. Yes, I know I could use Desmos, but I mean, why bother? Well, I'm going to use Desmos for the last bit because, you know, I want to do that. All right, so 1,960,000 times 2 minus 3/2 plus 2/3. There you go. So it's 2,286,667 joules.